Good morning, dear students. Today we can discuss about some of the important theories behind the nuclear stability. Or we have to discuss some of the important theory that will account the stability of the nucleus. That I already mentioned, there are various theories. Two are empirical theories, one that is N by P rule or N by P theory, and packing fraction theory, the two empirical theory, and more scientific theory are binding energy theory and nuclear attraction theory. So first I am going to discuss about the N by P rule theory or N by P theory of the nuclear stability. That is, according to this theory, it says that a nucleus is stable if the number of protons inside a nucleus should be equal to the number of neutrons present in it. In the case of the lighter nuclei of atomic number Z is equal to 20 or mass number A is equal to 40. This is the first statement of this theory. That is, the stability of a nucleus can be viewed from or analyzed from two viewpoints. One viewpoint is that those nuclei, in the case of lighter nuclei, the stability rule is that the number of proton and the number of neutron inside the nucleus should be almost equal to each other, or the N by P ratio should be equal to 1. The case of lighter nuclei. But in the case of heavier nuclei of mass greater than A40 or Z greater than 20, the number of neutrons should exceed the number of protons for stability, that N by P ratio should be greater than 1. So that is the two statement, two viewpoint of the stability in terms of N by P ratio. Okay, again, that is, according to the N by P rule theory, it says that when protons are added inside the nucleus, there arises a powerful pp repulsion, and in order to minimize the pp repulsion, equal number of neutrons should also be added inside the nucleus, so that the pp repulsion is on some way is counterbalanced by the Nn attraction or Np attraction that is produced due to the addition of neutron in between the proton. Okay, that is the core concept of the theory, is that in order to pack the nucleus, within the nucleus there should be another particle called neutron is to be added for stability. Okay, when neutron comes in between the proton, they will minimize the pp repulsion, or they will counterbalance the pp repulsion. So, in some way, the addition of the neutron inside the nucleus will give a stability to the nucleus by providing an attractive force between neutron and a neutron proton, and thus it will counterbalance the pp repulsion. And that is true. That is, in the case of a nucleus of mass A is equal to 40, this is the situation. That is, the number of neutron should be equal to the number of proton for stability. That is 4. Lighter nuclei, 4. Lighter nuclei of mass A, mass number A is equal to 40. So it's up to 40, or Z 20. The number of neutron should be equal to the number of proton for stability. For stability, the number of neutron should be equal to the number of protons, or N by P ratio should be equal to 1 for stability. This is A. The same case for nuclei of mass greater than 40 and up to okay, wait. The number of neutron should be greater than the number of protons for stability, that is n by p ratio. N by p ratio should be greater than 1 for stability. So combining these two, on combining these two rule, we can say n by p ratio should be or greater than 1. This is the n by p rule for stability. Okay, the argument is that when protons are packed together inside the nucleus, there is a pp repulsion. And in order to minimize the pp repulsion, neutrons should also be added inside the nucleus. So the additional neutron inside the nucleus create two attractive forces, N attraction and NP attraction. And these two attraction counterbalance the PP repulsion. That is a theory. Okay. So in order to counterbalance the PP repulsion, then neutron number should be equal to the proton number for lighter nuclei of mass number up to 40 or 80. For nuclei beyond that, the neutron number should exceed the proton number for the stability. That's the situation. For nuclei of mass greater than 40, the neutron number should exceed the proton number. So it is going on, increases. So that the n pi p ratio should be greater than 1 for stability. Okay. And this going on increase also when we go to heavier and heavier nucleus, it can be seen that the n by p ratio increases from 1 greater than 1, 1.3, 1.5, etc. up to something like that, 1.7, etc. But naturally, beyond the nucleus of mass number 200, they become unstable. They undergo spontaneous disintegration because in such nuclei, the number of neutrons is not sufficient to overcome the PP repulsion or the very large number of protons present there. Okay, that is the situation. The case of heavy nucleus of mass number greater than 200, the number of neutrons present in that nuclei is not at all sufficient to balance the PP repulsion, the strong PP repulsion arising from the proton together. So such nuclei will undergo the spontaneous disintegration, and they usually try to reduce the proton number by showing the alpha emission. So most heavy nucleus beyond mass number 200 are alpha emitting because they tend to reduce the proton number so as to increase the n by p ratio. They tend to increase the n by p ratio to the desired stability value. Okay, that's the situation. So most of the heavy nucleus with the mass number greater than 200 are spontaneously alpha emitting. Usually alpha emitting because they tend to reduce the proton number by emitting alpha. You know the alpha particle are packet of 2 proton and 2 neutron. So reduce the proton number by emission of alpha particle. So if you plot, that is the case, a graph is there, stability curve, N by P ratio curve. If we plot N by P as the y-axis against mass number A or number of neutron or mass number, both are the correct, or A or mass number. Number of neutrons, so the y-axis is N by P ratio value and x-axis is either the number of neutron or mass number. The plot is like this. This is the theoretical plot. There is a straight line passing through the origin at an angle of 45 degrees. It's an angle of 45 degrees, so that N by P ratio is equal to 1. N by P ratio is equal to 1. This is the theoretical curve. But in actual cases, up to mass is equal to 40, 50, 60, 70, 80, something like that, up to 90, 100, that is going on. Up to 200, mass number 200, that is actually the situation is that this is along with this line up to light nuclei, mass, beyond that it is going on increases. So all the nuclei, when plotted, their value fall within a belt. This is all the nuclei falling within this belt. All the nuclei falling within the belts, within the belt are stable nuclei. So in this case, you remember all the nuclei falls within the belt are stable. So all the nuclei above the belt and below the belt are unstable. So those the nuclei below the belt, the heavy nuclei, they will undergo spontaneous disintegration, alpha disintegration, by reducing the proton number. On the case the lighter nuclei, they are unstable. If the number of neutrons is greater than number of protons, they will undergo beta emission. So you have two extreme cases you have to look. Heavier nucleus undergo disintegration by emitting alpha particle so as to increase the N by P ratio. N by P ratio. To increase N by P ratio. While the lighter nuclei will undergo beta emission so as to bring the N by P ratio closer to 1. For example, in the lighter case, carbon 614. Carbon 614, this is a radioactive because your N by P ratio, carbon N, proton 6, but neutron number 6. So N by P ratio is 8 by 6. That is equal to Okay. 8 by 6, that is 1.33. But when it emit one neutron, it's a beta active, it will one neutron disintegrate to proton plus beta particle plus neutrino. This is the emission. So this is electron, this is a beta particle. So it is beta emitting, so that it comes to nitrogen, it is converted to carbon 614, now converted to nitrogen 714. Nitrogen 714. So that N by P ratio is equal to 1. So this becomes radioactive, beta disintegrating. So in the ratio now in the carbon 614 is 1.33 is now converted to 7 hydrogen 14 by the emission beta particle, and then by the ratio now become 1. This is simple case. Okay. So in the lighter nuclei, if they are unstable, they are usually beta emitting, and because of the greater number of neutron. Example carbon 614, they tend to reduce the neutron number by emitting beta particle. On the other hand, the case of heavier nuclei with the mass greater than mass 200, they are alpha emitting because of PP repulsion, so tend to increase N by pi ratio by emitting beta alpha particle. So that is the situation. So this theory is over, and this is an empirical theory. It is not purely scientific, it is purely empirical. Okay, so you have to remember generally like this: the stability ratio is N by P ratio is equal to or greater than 1. Okay, this is a general theory. For lighter, it is applicable for lighter nuclei, first thing, and for heavier nuclei, heavier, it is greater than 1. So it is applicable. So lighter nuclei it should be 1, but heavier nuclei should be greater than 1. I hope that you have followed this theory, you follow my class for this concept. Okay. So very simple theory. So you have to analyze that for lighter nuclei N by P ratio should be 1 for stability, and for heavier nuclei N by P ratio should be greater than 1 for stability. If they are not like so heavier nuclei, because alpha emitting, so they tend to increase the N by P ratio by increasing the number of proton by undergoing alpha emission. But in the case of lighter nuclei, if the N by P ratio is not equal to 1, usually greater than 1, they tend to undergo emit beta particles, so reduce the number of neutron there, and N by P ratio now become equal to 1. The next is packing fraction. The next theory is the packing fraction. PF as introduced by Aston. This term is introduced by Aston. Okay, what is packing fraction? As in name itself, it says fractional quantity that arises due to the packing of a nucleon together inside the nucleus. Okay, that is the terminology comes like that. Okay, you know that the actual mass of any atomic nucleus or any atom is the average of the isotopic mass of various atoms. You know that most of the atom exists as isotopes. So that is an atom can exist in more than one atomic form of different masses. That is called isotopes. Same atom can exist in different atomic forms of different masses. So the actual atomic mass of the nucleus is usually taken as the average of the isotopic mass. Average of the isotopic mass. Therefore, what I have to mention is that the actual mass of an isotopic nucleus or an atom is a quantity that is not a whole number. It is a quantity that is closer to a whole number. Okay. For example, oxygen 15.999 is not 60. Similarly, carbon 12 point something, not something. So when you look into any iron 54.999 something, or not exactly 55. So what I want to mention is that the actual isotopic mass of any atom or nucleus is a quantity that is not equal to a whole number, but it is a quantity closer to a whole number. It is closer to a whole number. Okay, in the form of a fraction. But the sum of the proton and neutron, which is always the measure of the mass of the nucleus, is always a whole number. So that's the thing. That is called mass number. These two different aspects you have to follow. That is the case of most of the atom or atomic nucleus, its actual isotopic mass is not a whole number, but it's a quantity closer to a whole number. But the number of proton and neutron present inside the nucleus, it is called the mass number, is always a whole number. So we have two quantities. One is the actual mass m of the nucleus, and we have the another number a, the mass number. This is the actual mass m, and this is the mass number. Second is the mass number a. This is always a whole number. Mass number is always a whole number, but actual mass is not a whole number, a quantity, closer to a whole number, closer to a whole number. As I mentioned, for oxygen it is 50.999, carbon it is 12.00, something like that. For hydrogen 1.0008, helium it is 4.0025, something like that. So not a whole number, but you have to remember the mass number is already considered as the mass of the nucleus, which represents the mass of the nucleus. Okay, mass number represents the mass of the nucleus corrected to whole number. That is called the number of the proton and neutron, which is called mass number, which is always whole number. Then the difference between the actual mass and mass number divided by mass number, that ratio is called a packing fraction. The packing fraction is equal to the difference between the actual mass m minus mass number, that difference divided by a, the mass number. So the ratio of, okay, this difference is always, this ratio is a very small value with no meaning, of the order of 0.0000 something, 0.002, 0.0004, 0.0003. Okay. So in order to make it a meaningful value, it is to be multiplied by 10 raised to 4. So this term is called packing fraction, introduced by Aston. So what is packing fraction? A packing fraction is a term introduced by Aston, which is defined as the ratio or the difference between the actual isotopic mass of the atom and the mass number to the mass number of the nucleus or atom multiplied by 10 raised to 4. So, or you can write in the form of an equation. Packing fraction is equal to m minus a divided by a into 10 raised to 4. Where m is the actual isotopic mass of the nucleus, which is a quantity closer to a whole number, or it is a quantity with a fraction, while a is always a mass number. Okay, and 10 raised to 4 is a quantity that is multiplied to make it a meaningful value. So we look into that. What is how the packing fraction changes? Okay, a nucleus can have packing fraction value either positive or negative. Okay, you have mentioned that it has seen that those nuclei with a negative packing fraction are more stable, while those nuclei with the positive packing fraction are usually unstable. So this is the situation you have to study. Okay, what I mentioned. What is packing fraction? The term packing fraction introduced by Aston is defined as the difference is the ratio, or the difference between the actual isotopic mass and the mass number to the mass number multiplied by 10 raised to 4. So that is equal to m minus a divided by a into 10 raised to 4, where m is the actual isotopic mass of the atomic nucleus or atomic mass, which is a quantity closer to a whole number, not a whole number. A is the mass number, which is always a whole number. So that difference is a fraction divided by a into 10 raised to 4 to make a meaningful value. That is called a packing fraction. Generally it is seen that those nuclei with the positive packing fraction are generally unstable, and those nuclei with the negative packing fraction are stable. So when you plot the packing fraction of various nucleus against the mass number A, so this is the packing mass number A and this is the packing fraction, okay, that is A minus A divided by A into 10 raised to 4. When it is plotted against A, they found that this is the zero value, okay, this is the packing fraction, that is 0. So the value is like this, the variation of this value is like this, okay, it's like to look at it is like this, and nearly about 40, 50, it become negative and is going on, increases in the negative fraction and beyond 200. It again become this is okay. Also, I am writing this. So we can see that on plotting packing fraction, this is negative and this is positive and this is 0. If we plot the packing fraction, we plot packing fraction versus mass number A, the situation is that, or the variation is such that packing fraction of the lighter nuclei positive and it crosses 0 and becomes negative, and the negative value remain as such as a broader negative value, and beyond 200 it again crosses 0 and becomes positive. It means that all the nuclei, lighter nuclei below, lighter nuclei are unstable, and all the nuclei beyond mass number 200 is unstable. So all the nuclei with the mass greater than 200 is unstable. That is usually the case. According to observation, they are spontaneously radioactive. While the lighter nuclei, it is not unstable as cited by the packing fraction, because the packing fraction value oxygen 16, carbon 6 to 12, 2 He4 do not fall in this curve. So they are otherwise very stable. This is 2 He4. 2 He4, carbon 614, carbon 612, oxygen 16. All this does not comes here. So they are much, they will not fall in these curves. So hence they are said to be stable. But all other nuclei with a mass greater than 2 or 20, okay, mass greater than 20 or approximately 40 like that, they become stable because their packing fraction become negative. So the stability of the nucleus, those nuclei having packing fraction negative, they falls in a broader region, that is from nearly mass 20 to nearly mass 200. So how it is stable at account? Those nuclei with the negative packing fraction is stable. So according to packing fraction theory, according to Armstrong, we can see that when a particular nucleus is formed by the assembly or the packing of the nucleus and proton, it is seen that some amount of the mass is lost in the form of energy. Some of the mass of the particles are released or lost in the form of energy during its formation. Therefore, the actual mass M is found to be lesser than A, that the mass, sum of the mass of the nucleon. So that is the situation. That is, when a particular nucleus is formed by the assembly of the constant particles of proton and neutron, okay, some of the mass of the proton and neutron is lost and it is released in the form of energy during the formation, not at instability. Therefore, the energy, the mass that is lost is converted to energy. So the actual mass M is become lesser than A. So that M minus A is become negative. Okay. This M is less, become less because the mass that is lost during the packing of that particular nucleus is released in the form of energy. That is M minus A, that is delta M, that is released in the form of energy E is equal to delta M C square according to Einstein mass energy relation. So according to Einstein mass energy relation, it is seen that the delta M that is lost is released in the form of energy E, delta M into C square. That will become, they are stable. But this theory is not at all not fully correct, because we cannot account for the stability of 2He4, carbon 6 tall, oxygenate 16, all such nuclei, in spite of their positive packing fraction. They are very stable, but they have positive packing fraction. Okay. Similarly, we cannot account merely by saying that certain nuclei like uranium etc. are unstable because their packing fraction is positive. There are various other reasons. So we have to say that this both packing fraction theory is also empirical. So we got a general idea or overall idea of the stability. So I hope that you have followed me. The packing fraction. Don't forget to confuse the packing fraction. It is the actual mass M, isotopic mass M, which is a quantity closer to whole number, minus mass number is a whole number, divided by A into 10 raised to 4. So 10 raised to 4 is a multiplication factor in order to make it a meaning. Otherwise, it's very difficult to memorize that difference. 0.0 M minus A by A. The result is 4, something like that. So it is very difficult to remember. So when multiplied with 10 raised to 4, you get the value as 2, 3, 4, 1, etc. Okay, like that you will get the value. That is why we are multiplying with this. Then the stability, positive packing fraction is there. Nucleus negative packing, most of the nuclei comes under the negative packing fraction. They are stable. Between mass 220 to 200 are negative packing fraction. The lighter nuclei, they are positive packing fraction, but they are stable. That cannot be explained. And those above 200, they are unstable because they are positive packing fraction. Okay, time being, I am winding up my class. So next class we will discuss the most modern or most scientific theory. That is the most conceived theory. That is the most scientific theory. That is the binding energy concept. And after that we can discuss the nuclear force attraction theory suggested by Yukawa. Okay, thank you very much.